My name is Devin Ripner, and I'm going to talk about integrating multimodal imaging to enable chemically informed segmentation of X-ray computed tomography data. I've worked with a ton of people on this. Many of them are listed here, and I'm very grateful for all their efforts. This is not like a single person type of job. Like, this takes many people working full time to make any progress. And so I'm going to lead with this picture that Odetta and Victor took of a soil aggregate. On the left is the SEM image, and on the right is the corresponding CT scan. You can see the alignment is okay, but there are errors, and we'll talk a bit about that. But I'm a soil scientist, so I do need to kind of lead with talking about why imaging soils is challenging. Soils are incredibly diverse. There are 20,000 soil series in the United States. That's about the same number as there are vascular plants. So they're very diverse. And here's just some of the examples here. You can see that there are little critters in some of the soils, and there's roots, and the soils have different colors and textures and different components to them. Most soils are opaque to visible light, and they contain almost every element and particles ranging from nanometers to, more than meters. And wouldn't be soil though. The top meter of soil contains about 2,200 petagrams of soil carbon, and so that's our largest terrestrial source of carbon. And understanding the spatial distribution of carbon and other elements is crucial to understanding carbon transformations due to management. So things that we can control, right? We want to control carbon accumulation. We'll go back. A lot of people have kind of brought this up, but scientific imaging is very important to the BER community. And it's because it provides unique spatially explicit data. And the information contained in any image is really dependent on the light source, right? Your sample and your detector. So not all light sources are compatible. So you wouldn't use like a RGB camera detector to capture gamma rays, right? It'd go right through it, or X-rays. And so you really want to make sure you match your detector and your light source, but your sample also has to be matched, right? So some high energy imaging environments can damage your sample. You know, you shine bright enough X-rays on something, it will start to burn, will change. And so it's really important to consider sample preparation as you're getting ready to image, right? You don't want it to change too much. Now, I use X-ray computed tomography frequently. I really like it because it gives great insights into 3D structures in soils that I normally can't look into. Now, soils are interesting because they're composed of materials with various X-ray absorption characteristics, so you can get beam hardening. And especially with polychromatic beams that you find on benchtop scanners and even white beams at synchrotrons, you're going to get beam hardening, which can make it hard to see contrasts. And so here's an example. This is actually the first soil aggregate scan I ever took at the advanced light source. And I didn't know what I was going to see inside of it. I've been scanning oak wood for, I don't know, the whole day. And let's see. So here it's playing. You can see there's lots of minerals and stuff. But oh, that's actually oak wood inside of that aggregate. And the only reason I recognized it is I had spent the whole day looking at oak wood before I scanned this aggregate. And this was a real eye-opener for me, that there can potentially be very large objects that are not mineral or pore inside of very small things, and that we should probably be able to segment that and capture that data. And so historically, XCT scans are often split into binaries, right? Solids and pores. I'm going to show you an example of that. This is a soil column. So you can see the pores, lots of big pores in here. And then in gray are the mineral solids. But as it turns out in this scan, those giant pores aren't pores, they're organic matter. And I bring that up because it's really important for understanding flow characteristics, right? If you take out the 50 biggest pores from a column, all of a sudden the flow characteristics are going to be very different. So you can see the organic matter spread in there. So this is the actual scan. You can see there's giant chunks of organic matter actually at the top. They're not pores. And so my team has gone through and hand annotated these, and we've trained neural networks to segment organic matter out of columns and aggregates and do all this stuff. And it's been fantastic. But the reality is, how do we know what we're looking at? How do we know that we're seeing an organic or not? Right? I figured that was a piece of oak because I'd spent a day looking at oak wood under a micro CT. But then there's other things in this image that I don't know what they are. I've marked this as organic, but I don't know what it is. And this is obviously a unique mineral phase here. It shows up differently than everything else. It's absorbing a lot of X-rays. I didn't even try to mark that, but I can train a computer to replicate what I do pretty well. But as I said, I often look for the weird stuff in scans and mark it as organic matter. But as it turns out, if you answer look for the weird stuff in your scans and try to annotate it as organic matter, oftentimes it won't be. So this is something that to me would maybe look organic, but it turns out it's an aluminosilicate, right? And so I can't mark this as organic. This was a real eye-opener for me. Like I potentially am making a ton of errors as I'm annotating these images. And so this leads into kind of a workflow that my group has done with Tomas and Odetta and a number of other people to try to like actually look inside of soils and soil aggregates and figure out what they're composed of, right? So I'm going to go over a little bit about our attempts at embedding aggregates and then our attempts at analyzing the data that is coming from this analysis. So I'm going to start. We originally tried to embed aggregates in sodium metasilicate. We figured that this would be a non-carbon source to embed our aggregates and that we could then directly identify carbon compounds by FTIR microscopy, and we could directly identify carbon potentially by SEM EDX. This was a failure. And so one of the problems here is the sodium metasilicate, when it hardens, makes pores that have no contrast compared to the mineral solids around them, right? And you see that we don't even get complete, like, it stopped on the outside. It didn't penetrate. The silicate didn't go in. So we have very poorly embedded aggregates that were so rough we couldn't do SEM or FTIR microscopy on them. And so this was failed. I tried to train a neural network to segment it, and this is kind of what it looks like. This is the aggregate. It just looks like a ball of silicon with some pores inside, and inside there's some organic matter. My model said there was organic matter, but it looks terrible. So that just didn't work. So then we decided to try different stains so that we could do like chemical imaging by XCT or then do multimodal imaging using SEM EDS. And so I'm going to go into that. I'm going to talk about our I2 staining first and dual energy micro CT work. And then I'm going to talk about our osmium staining and some of the micro CT and SEM EDS work that we're doing. Okay, so my group tried staining samples with iodine. These are aggregates inside of glass fiber filter bags, and they're being exposed to iodine solid, which turns into that nice pink gas. And so this actually worked pretty well. We imaged at 33.1 and 33.2 keV right at the X-ray decay edge for iodine. And so we were going to train a model based on the difference image from those stacks. And the difference image should contain iodine absorbing compounds. Now, there are some challenges to this. As it turns out, iodine is soluble in most solvents. And so as you're fixing these, you can watch the iodine come out of your aggregates, which is a little creepy. So here's an example of the difference images. This is one of the best examples. And so on the left is below, and the right is above the K edge. And so here's our difference image, right? So this is where there's an accumulation of iodine. I should use my pointer for this. So there's an accumulation of iodine here, a couple other spots here. And so we were able to turn this into a mask. Did this for a number of these samples. I think my team probably annotated 15 images. And then we turned it loose on some different samples just to see how it do. So here's my first scan for the advanced light source. The model that we developed was able to pick out the mineral solids and pores relatively well, but struggled with the organic matter. It's not stained, so it's not surprising. The middle three are what we kind of trained off of, and we get pretty good predictions on that. And then on the far right, so you can see there's big chunks of organic matter in these. And then on the far right, we're not able to pick up the organic matter in the silicon embedded aggregate. But this, for a model trained on 3 aggregates, we were surprised. I was surprised at how well this did. This is the result of the model on one of those aggregates. So in gray will be mineral solids, in brown is organic matter, and then pores that are connected are the same color, and pores that are disconnected are different colors. And so what we see is actually a lot of the pores in these microaggregates or aggregates are connected, but there are microsites around the organic matter. And these are, it's pretty cool that there's microsites around the organic matter, because then you can think about like iron reduction or redox processes actually changing the carbon there. So it's, it's fun to see this. I'm really excited to expand upon this work. I certainly would like to build upon this and apply this to a whole slew of aggregates. So the iodine work went okay. I think one of the biggest strengths of it is the ability to potentially train 3D UNets on like big chunks of data, where you just use the difference image and you have this like 3-dimensional chunk that you can train a 3D UNet with. But it only gives you the location of carbon functionally, right? So that's where the SEM EDS comes in with the micro CT. And I think I'm pretty much well, I'm a little bit behind everyone else here. So this is a work in progress. Part of it is I didn't have the Oxford software. I decided, oh, I'm going to just use the raw data. Each slice was 1.8 terabytes of raw data. And I think there's like 60 of them. And so it was too much for me. I now have the software, everything will be better, but the reality is this is a big data problem, right? This scan right here is in its raw form when I reconstruct it is 496 gigabytes, right? I can't open that in RAM on my computer. It's, and so we really need to find ways to prune data, get things as small as possible for training neural networks. Let me keep going. So, I see this being really possible. I would love to train off of the masks that are generated by the SEM EDX, but I'm actually also okay not using those masks for training and actually continuing to hand annotate aggregates, using those masks to confirm what I'm annotating, right? I don't need perfect alignment, but I know that this piece right here is organic matter. Even though it looks a little bit different than that scan, I can still mark that piece as organic matter and pick it up with my neural networks. And so that's something that I would like to do as we're getting to this, the image registration problem is real. I think prior to that, we can use the information from our scans to hand annotate, and it's like a improved human version of this. So I think that is a way forward in the short run, though, registration is crucial. Being able to register SEM scans directly to CT scans will, pick up the speed of this stuff. So here's some examples of iron inclusions that we can see. Again, have similar problems to other folks where part of the scan, let's see up here, we get relatively good alignment, say between these two spots, but then down low in our scans, we just have image registration problems. This is a continuous challenge. It's nice to see everyone bring this up. I'm like, oh, it's not just me, thank God. So to wrap this talk up, so multimodal imaging is crucial for correctly identifying components in CT scans. I think it is the future. In our work, metasilicate fixation was a failure, but other types of fixation worked really well. If you would like to ask me any questions about fixing samples, I'm happy to share my experience. And so I'm really excited to keep this going forward with both iodine and osmium staining. I think they fill different roles potentially. And then I'm excited to turn this loose. There are a lot of soil aggregates out there that are pretty different looking. This is from an andesol. This is from a histosol. I don't know if we'll ever be able to like segment odd soils really well. You can see, so this might look organic, but it is 100% volcanic. And so that's just a silicate up there. And so I don't know if we'll ever, be able to segment those extreme examples, but I think that we're getting to a point where we will be able to segment organic matter from visible organic matter from almost any CT scan, and then potentially segment other chemistries. So yeah, I think the the end goal or a very necessary component for all of this work is people working together to share data, share their experiences, share where they've made mistakes, and then hopefully we can like build something that a variety of users will actually use. So with that, thank you so much for your time. Yeah, I've worked with a lot of people to get to this point.